Hello everyone, this is Algebra for Life and we're going to solve an eigenspace and eigenvector problem. So, this is the headline for the problem. We've got an endomorphism in R3 with this application, and they ask of us to find the eigenspace for the application. So, let's start with finding the associated matrix. We've got the base here, B, which is E1, E2, and E3. E1, more or less. So basically, E1 is 1, 0, 0. E2 is 0, 1, 0. And E3 is 0, 0, 1. So we got this base, and now we need to applicate this. So F turns into this. So we've got F of E1, F of E2, and F of E3. So let's see what they turn out to be. So we got for x1 a value of 1, x2 a value of 0, and x3 a value of 0. So x1, x1, and x3. So what's the deal? We got 1, 1, 0. 1, 1, wait. 1, 1, 0. For E2, it's for x2. So 1, 1, 0 again. 1, 1, 0. And for E3, only 0, 0, 1. So now, how do we find the associated matrix? Easy. So now we got the application set, we got the 3 vectors, and now placing them in the correct order, we got the associated matrix, which is F of P. This is the associated matrix. Okay, now we think we can find the eigenvalues and the eigenspaces. So first let's start with the eigenvalues. Let's see. We got the associated matrix, now we need to find the eigenvalues. So how do we find the eigenvalues? Easy. We got this formula here, we apply it. It's F, which is the associated matrix, minus lambda times I, which is the identity matrix. This equals 0, okay? So let's get right into it. The thing is, we got here an equal, okay? So we go here, and to the associated matrix, we subtract this. So it is 1 minus lambda, 1, 0. 1, 1 minus lambda, 0, 0, 0, 1 minus lambda. Okay, so these are actually, this is actually a determinant. So let's change the oblique bar for as variables. This, much better. Okay, so now we need to find this determinant. So how do we find it? We have to find the determinant and get a third grade equation in which we got the roots for. We have calculated the determinant here, and we got these 3 eigenvalues. Now, each of the eigenvalues has an order of multiplicity of 1. This we're going to use later, you'll see. So let's get right into finding the eigenspaces. The eigenspaces are obtained from the eigenvalues in this way. So, eigenspaces. So, to find the eigenspaces, we need to apply this formula here, which is the associated matrix, minus the value of the eigenvalue you need to find the eigenspace of, times the identity with an unknown matrix, which will be the one we use to find the values for the base of the eigenspace. All this equals 0. So, we got, set the example here, for lambda 1, which was the first eigenvalue, we had a value of 0. So, this value was 0, and we can see it here in the formula, associated matrix minus lambda 1, which is 0, times identity, times the unknown matrix. So let's get into it. So the matrix was 1 minus 0. 1, 0. 1, 1 minus 0, 0, 0, 0, the unknown matrix, which will be x1, x2, and x3. So, all this equals 0. What do we get out of here? So, we multiply these two matrices, and we got x1, x2 equals 0, x1 plus x2 equals 0. From the second, we obtain the same, x1 plus x2 equals 0. 0. And for the third, we obtain x3 equals 0. So we got the equations out of this formula, as we've seen, all this equals 0. What happens here? We got two repeated equations. So we cross out one. So we got two equations and three unknown values. This is 1 degree of freedom. So let's see. x1 plus x2 equals 0 and x3 equals 0. Let's get this thing prettier. x2. Okay. So now we're going to find how many parameters do we need to add. It was 1 degree of freedom, so it's one parameter. So x1, as you can see, we can call it alpha, for example. x1 equals alpha. x2 will be minus alpha. And x3, as we saw, it's 0. No big deal, of course. So let's see. All this we can put it into the eigenspace, which will be S of lambda 1 equals the combination of alpha minus alpha and 0. So if we have a base for this is the actual parameter form for the eigenspace. We need to find a base, and a base for the eigenspace, which will be S sub b of lambda 1 will be. So we take any value for alpha, but in this case we're going to select the easiest one, or the most simple, which is 1. So what's the base? The base will be 1 minus 1, 0. Okay, so this way we got the first base for the first eigenspace. So now we're going to calculate the second eigenspace following this same procedure. Now we find the second eigenspace, which is this formula here. We reapply it again, and we have to apply it with lambda 2, which was the second eigenvalue, which had a value of 1. We can see here the formula, lambda 2, which is 1. This is the Ejercicio matrix, 1 times the identity, and the unknown matrix. This is what we have here, times the unknown matrix equals 0, and we got these three equations here. So, obviously, x1 is going to be 0, x2 is going to be 0 as well, and what happens? x3 is not here. What happens with all the values that are not present in the three equations? They are parameters automatically. They can be any value. So this is alpha. Now, the space will be 0, 0, alpha, which is generated by 0, 0 alpha. Give me a second. People have to deal with every day. Okay, so now we got this space here, and we assign a random value to alpha to obtain a base for the eigenspace. We're going to choose again the simplest value, which is 1. So the base for the lambda 2 eigenspace is going to be 0, 0, 1. Okay, now we're going to go into calculating the third eigenspace. We're going to calculate the third eigenspace, which is applying the same formula here. And now, what do we have? We're going to apply the formula for the third eigenspace, which is lambda 3. We're going to noted here. And we got the formula here, associated matrix minus lambda 3, which had a value of 2, times the identity times the unknown matrix equals 0. So this is the resultant of all this equation. Now we gotta make sure we got the 3 equations here. So we got minus 1 and 1. So here, minus x1 plus x2 equals 0. Now we're gonna find the second equation, which was the same as the first one. x1 minus x2 equals 0. It was the same as the first one, but the signs are changed. They're proportional, so one of them is going to go out, definitely. And now we got the third equation, which is x3 equals minus x3 equals 0. What do we get out of these equations? Well, as I said, these two are proportional, so one of them has to go. This one, for example, because it's the one I like the least. Doesn't matter, you can choose whichever you want of these two. So, we got 2 equations, 3 values, 1 degree of freedom. So, that's it. x3 is going to be 0, no big deal. And what's x1 and x2? Well, we can assign one parameter to x1, for example, which is going to be alpha. And x2 depends on x1, so it's going to be alpha as well. Because x1 equals x2 here in the equation, so they are both alpha. So, the space is the one generated by alpha, alpha, and 0. Let's get it prettier again. Alpha, alpha, and 0. This is the eigenspace. Now we're going to find a base for the eigenspace. The base for the eigenspace, we assign a value to alpha. Again, the simplest one is going to be 1, 1, 0. Eigenspaces, we've got a base of each eigenspace, and the problem demanded for us to find the eigenspaces and the dimension for each of them. So, for the 3 spaces, the dimension is going to be 1 because they only have 1 degree of freedom. So here we have listed for lambda 3, the dimension of the eigenspace associated to lambda 3 is 1. Same goes for the dimension of the space associated to lambda 2, which is 1 again, and same goes for the dimension of the eigenspace associated to lambda 1, which is 1. So now we've got a dimension of 1 for each of the 3 spaces. Now, recall the order of multiplicity of the eigenvalues. It was 1 for each of them. So it turns out to be that the order of multiplicity for lambda 1, the order of multiplicity of lambda 2, the order of multiplicity of lambda 3, they are all 1. And actually, the other values for the dimension of the eigenspaces, they are all 1 again. So this equals to the value of the dimension. So this means that since all 3 values match, the resultant matrix is going to be diagonalizable. Okay? So it turns out to be that f of b B is diagonalizable. So this is the exercise. I hope you enjoyed it and it turns out to be helpful for all of you. This is Algebra for Life again, and I hope you enjoyed it.